All right, welcome scholars to the second to last lesson of the year. And these last two lessons, we're going to spend a bit of time talking about limits, which is an idea that will help you kind of get a head start in calculus should you choose to take that class, whether it's now in high school or maybe later in undergraduate, should you go into a field that requires it as a general education credit or otherwise. Okay, so we're going to talk a lot about these things in the 1 week we're going to have. They will appear on the final. So let's go ahead and talk a bit about these. All right. So first of all, what are limits? Well, limits are defined as a value that a function y, that is f of x here, approaches as the x input x approaches a certain value. So if you kind of back up and read the statement a couple of times over, it's basically saying as I pick a y, or as I pick an x from my function, this limit just describes the value that it would be at that point x. Okay, so you're kind of thinking about what I just said, and you're like, that doesn't sound any different from just evaluating the function is true. And you're probably right, okay, which I'll show you in the examples. But here's some notation, and this notation is very important because there's going to be a distinction between evaluating the function at value x versus not. Okay, so let's take a look at this notation here. I'm going to prep my pen here. So first of all, okay, we've got this idea, okay, that we have a limit right here, okay, as, okay, that's the blue part, and don't worry, I'll box it all in as I go along. X approaches C of f of x equals L. Okay, so let me go ahead and box all these for you so you kind of know what part of the notation I'm talking about. Here's the equals L part. Here's the f of x part. Here's the x approach C part. And finally, here's the limit part. Okay, so this is how we read the notation. It is not very apparent, which is kind of why I went ahead and marked everything out for you. But x approach C with the arrow, that indicates what value are we taking at interest with our x. All right. So for example, if I want to look at where the function approaches as x approaches maybe 0, I'd be looking around the places where x is 0. Okay, right, and it's so on and so forth. For example, if I'm looking at x equals 5, okay, x approaching 5, I'm going to be looking around the x equals 5 area. Okay, cool. And of course, this L at the very end is referring to where's y, okay, when you are around that area. Okay, and I'm using all these kind of vague words like approaches, around. There's a reason for that. Let's get into some examples, okay, of some graphs and take a look at maybe some limits and defining those limits. Okay, so here's our first example, and this is probably going to happen in most cases, okay, when we're looking at graphs that are continuous, right? This is the kind of graph we're most comfortable with. There is no hole. It's just a nice, complete line, a nice, complete thought the whole way through. So here's our question. As x approaches 1, what does y approach? Okay, if you want to think about this in terms of the notation we were looking at, we're talking about limit, as x approaches 1 of f of x, which we don't know what the equation is, equals what? That's what the what part is. Okay, so let's take a look at our graph. I said we need to look at where x is equal to 1. That's probably around right here. Okay. Now, if you are pretty good at reading graphs, which I assume most of you are, you might say, oh, Mr. Hu, that's about negative 1.5, right? This is about negative 1.5. Negative 1.5, however you want to call it. Okay, so that'd be pretty much where you're looking at, right? And in this case, we are going to set our value as negative 1.5, because that's where it happens to be on the graph. Now, if you're sitting there behind your screen and you're like, wow, that seems really easy. There's nothing else to this. I am going to tell you, not really. Okay, If your graph is continuous, okay, and it asks you as x approaches some value, what does y approach? You're pretty much always going to pick the value that it is actually in the graph because, well, it's defined, right? So we don't need to really worry about different cases where that might not be the case, which is what we're going to look at next. Okay. Now let's take a look at the next question. Okay, here we have a new graph. Okay, same question. As x approaches 1, what does y approach? So I'm going to write that statement out one more time here again. Okay. Limit as x approaches 1 of f of x equals what? Okay, well, there's a difference here, right? You can see that our graph is no longer continuous, so it is a discontinuous function. Right, hopefully you remember that from Algebra 2 and all the various discontinuities we have. That includes like asymptotes, holes, that kind of thing. Right, if you don't remember that, you may have to maybe dig those notes out. Okay, I won't be talking about them too much, but hopefully you remember that the not filled in hole is a hole. The not filled in dot, sorry, is a hole, as in a removable discontinuity, and the actual filled in hole is the actual value. Okay, so as we look at this graph, I'm looking around the area where x is 1, right? So here's our first area, here's our second area maybe. Okay, this is about 3/4 maybe, or 0.75. This one's maybe like 2.25, okay, or however many fourths that is. I think it's 9/4. Okay. And you might be saying, okay, Mr. Who, I see that the bottom dot is colored in, right? So I know that f of 1 is equal to 3/4, okay, which is what I'm kind of assuming the value to be. It may not be after all, but I'm going to assume that way. Okay, so you might be like, all right, I'm going to say this is 3/4 then, because, well, that looks like the value of the function at 1. Okay, well, we are approaching 1, okay, from a direction down here. It's from the left, right? So from the left, we are coming up to this value 3/4 at x equals 1. So, in order to note that on our notation, we need to use this minus sign, okay, to indicate that this is from the left. Okay, cool. So far, so good, I think. That's pretty intuitive, I think. But let me take a look. There seems to be another point, right? A hole. What do we do about that? Well, just like there's a limit from the left, so too there is a limit from the right. And I kind of overlapped it a little bit, but let me move that out of the way. Here we go. Okay, moving that out of the way. Let's take a look at from the right. Well, if I'm coming from the right, that is, I'm coming from this direction, okay, I can see that the value is approaching the hole instead, right? If I trace along the graph long enough, here's my graph, and I'm coming to this hole point, which is 2.25. Well, we can still describe this as a limit, okay, and this is going to be like 2.25. I think that's 9/4, so I'll put 9/4. It'll be a little consistent in the presentation. Okay. However, because we're approaching from the right, we need to notate this with a plus. Okay, so as we approach 1 from the right, okay, our limit is 9/4. As we approach from the left, the limit is 3/4. Okay, so what's the big idea here? We have two different values. Which one is the actual limit? Well, this is where limits get a little tricky. Okay, remember, limits aren't actually the value of the function if your graph is continuous like this. So we need to actually check our work. Are these two values equal? Well, you're sitting back there and you're like, well, those definitely don't look the same, right? They don't look like the same point at all. Since they don't end up at the same point from the left and the right, we say that the limit as x approaches 1 overall of this function does not exist. DNE. Okay, so when we approach from the left, we might find a value. When we approach from the right, we might find a value. But in order for the actual limit to exist overall, they need to be the same. And if they're not, then the limit doesn't exist. Okay. This is a little different from what we thought about our definitions of function values being defined or not defined, and all that kind of stuff, right? So we have to keep that in mind as you go through the IP later. Okay, so here are the key ideas to take away from our notes here today. A limit is a value, but not necessarily the one that is defined on the function. Okay, I'll kind of show you an example of this real quick. We saw two different graphs, but here's another type of graph you might see. If I draw a nice little curve, well, it would have been nice if it didn't mess up there in the middle. Okay, but I'll say I draw a nice little curve, and I put a hole right here, and a point up here. Okay, here's the value of the function. Here's the limit of the function. Okay, so just be careful when you're looking through the notes and looking through the Delta Math modules, because your limit does not always have to be the value. And if the question asks for the value instead of the limit, you'll have to think about the value and not the limit. So just kind of keep that straight as you go through the Delta Math modules. Next, there are two sides to approach from, the left and the right. Make sure you're notating these correctly, okay, with minus and plus as you read along with the modules and stuff. And for a limit to exist, the left and right limits must be equal, otherwise it does not exist. All right. Again, we're only talking about graphs. We're not talking about the mathematical tables and stuff. Wait until the next time. Okay. But hopefully this got you your feet a little wet with a little bit of things we need to start learning for calculus. This has been Mr. Hu. I will see you guys probably next year, because I think Miss Atkin is going to do the last one. But it's been a wild ride, and hopefully you come to class with questions about this, and we will talk during then. I'll see you then.